So welcome from my side. My name is Andreas Schwope and I'm working for Renesas Electronics in the Smart Factory Group, where we have lots of industrial automation devices. I will show you that with our chip you can have a simple cost-saving solution for network compatibility of your product. So Industry 1.0 was introduced by the machinery, which was saving a lot of work. Industry 2.0 was a step in which electrical power was introduced into this machinery and make the work much more softer. Industry 3.0 was a step in the 1970s, which was introducing electronics and IT into the machinery, which makes it very simple to work and reduce a lot of effort. Now we are stepping into the Industry 4.0. This is an introduction of so-called cyber physical production systems. So what does it mean? So there are some areas in the industry which are now put together in the Industry 4.0 arena, such as sensor networks, communication, actors, embedded software, big data and the computation of those data. And everything is put together in an automated operation to make it very flexible for the factories. R-IN32M3-CL. So this is the device for the industry applications. So here I will show you which area this device is targeted for. Fabrication network is normally divided into three parts. So we have a controller network, we have a field network, and at the lower end we have the sensor network, where we have electronic components which are serving sensors and actuators. And exactly here is our target application of our R-IN32M3-CL. The following slide now shows the details in terms of a block diagram. So you see the CPU with the memories, the multi-master bus, where you have lots of IPs which are serving interfaces and controllers. This foil shows you the details about the CPU setup. So we have a 100 MHz Cortex M3 CPU with 768 KB instruction memory and 512 KB of data. We have interrupt controllers and these kind of things which are normally inside this typical SoC structure. On top of this, we have hardware accelerators. The network area is now composed out of a 2-port gigabit switch with MAC. We have Ethernet accelerators which are serving functions for frame processing like CRC calculation, header encoding, decoding, and also buffer management. The network features: we have a CC-Link IE field controller. We support with the standard Ethernet setup a wide range of industrial Ethernet protocols. Our switch supports cut-through and store and forward functionality, and also IEEE 1588 for the precision time protocol. This is now showing the peripherals. So connected to the multi-master bus, we have things like DMA, we have general ports for GPIOs, we have a CC-Link controller, we have ROM and SRAM memory interface, which can also be used in the opposite direction as a host interface for an external CPU. This all comes in a compact 324-pin BGA package, 90 by 90 millimeters, with a 1 millimeter ball pitch. We have boundary scan support. The clocks are generated by a 25 MHz oscillator, and power supply we have 1.0 and 3.3 volts. So let's go to the requirements we need to support in a factory environment. So you often hear about stable operation. You need a high accuracy system operation. You need real-time response and high-speed task change. And everything needs to be supported in a very low power environment. When breaking this down to the software side, your software needs to have a task requirement of having task switches with low latency, with a low jitter, and when looking into a network, all network nodes needs to somehow behave in an isochronous way. You can do this with software level up to a certain extent, but if you want to be more precise, more faster, you need to introduce hardware. And this is exactly what we have done with our RIN32M3-CL device. We have introduced hardware accelerators on different levels. Here you see a software task environment which is based upon a standard traditional software approach, and in contrast to the RIN32M3 you see that the hardware accelerators are doing it much more precisely. They are doing it faster, they are doing it with less jitter, and when looking into the network they are doing this also in an isochronous way. So let's have now a look to the accelerators, a high-level look. So we have on the one hand side our Cortex-M3 CPU, which is closely connected to the hardware RTOS accelerator. We have the Ethernet frame accelerators, which are doing the checksum calculation, which are doing header encoding and decoding. And also we have dedicated buffer management for the frame processing. And last but not least, we have the CC-Link IE controller for the gigabit CC-Link IE field application. Now let's have a close look what the hardware RTOS is going to do inside the RIN32M3. In a traditional approach, you see here that the CPU is doing both. On the one hand side, the task processing, but on the other side also the operation for scheduling the task. You see that it takes some time to switch from one task to another, and also you see that the variation between the switching is sometimes different. On the opposite side, you see that the hardware RTOS is doing the task scheduling in a much more efficient way. The delay between switching from one task to another is much smaller, and this implies also that we have a small jitter here. The impact to this is that on the one hand side we got a higher performance of the CPU because of the unload, and everything is done also with less power because the task scheduling is done by hardware, which is much more efficient. As the hardware RTOS accelerator is a piece of hardware, there must be certain resources. Here you see the different functions which are supported by the hardware RTOS. It's synchronization and communications for event flags, semaphores, mailboxes and so on. Then we have task management. We can exit task, starting task, terminate task, wake up task and so on. We have the system status management to do some controlling over the CPU. We have the general time management. And on top of this, we have even certain functions which are directly controlled by interrupts and which can do these functions without the use of the CPU. So what is the outcome of this kind of architecture? So here you see an example for a normal frame processing. You see that the frame processing consumes about 30% for the RTOS operation, 30% for the simple checksum processing, and the rest for header, encoding, decoding, and memory copy, and such kind of things. In RIN32M3-CL, you see that most of these parts are accelerated by the accelerators. CRC checksum generation, RTOS operation, as well as header encoding and decoding. These numbers give a clear understanding about this acceleration. While on the one hand side, a comparable hardware architecture uses 165 microseconds for a UDP checksum generation, the RIN32M3 does this on the fly, which means the result is available directly after the end of the frame. Thus, it consumes for verification and generation of the CRC 0 microseconds. What does this mean in overall sense to your application? So with RIN32M3-CL, you can efficiently combine communication and application in one single device. While comparable CPU architectures can come up to 70 megabit per second, they are not able to process an application on top of this. On the other side, RIN32M3 is just loaded up to a factor of 31% for 100 megabit. If you go for CC-Link IE even higher, you can reach about 270 megabit before you are loaded at 100%. This means for your application that each unnecessary performance which is not required for the communication can be used for your application in this device. So coming now to what we can offer in terms of evaluation board. For a smooth solution development, you need the following things. For the hardware development, you need a simple structure first. You need some kind of evaluation or starter kit. You need the board schematics where you can use the circuitry for your own PCB development. On the other side, the software development requires an easy environment to build up your application. You need an application example which shows you how to include the CC-Link IE stack into your software environment. You need to start up code. You need the CC-Link IE and also the CC-Link stack in order to smoothly integrate this into your application. And everything about this has to be integrated in one integrated development environment. And last but not least, you need some kind of pre-performance testing which enables you without a big risk to do the certification of your device by your own. So let's have a look to the solution structure of R-IN32M3-CL. As we have here a cooperation with Mitsubishi, the Mitsubishi ASICs has been integrated into the RIN32. We have the CC-Link IE field controller on the one hand side and also the CC-Link field controller as a second interface. RIN32M3 provides also a very simple migration from a previous structure, which you see here on the bottom side, to the new structure. At the end, it's a very simple structure with just the RIN32M3 as a major device, plus external PHYs, which are serving the 1 gigabit of the CC-Link IE protocol. This is integrated onto our RIN32M3-CL starter kit, which allows you to simply develop your PCB on your own. This foil shows the starter kit. So in the middle you see the RIN32M3-CL combined with the ports for CC-Link IE and the CC-Link field bus. Around there are more interfaces to easily connect this board to your application. We have parallel interfaces, serial interfaces, and there is also the external host interface which allows you to connect an external system to this board which is able to directly access the resources of RIN32M3. So this foil now shows you what you can get with the starter kit. On the one hand side there is the board, on the other side the required protocols for CC-Link IE and CC-Link. There are also some application examples which allows you to easily integrate your application into the environment of the CC-Link IE stacks. Having a look to the software package of our starter kit, you see that we have a lot of sample programs. We have a CC-Link IE sample program. We have some more simple application examples which are showing you how to integrate your application together with an OS. And we have also an application for an OS-less sample. Integrated into this package are also the CC-Link IE and CC-Link stacks. We have middleware for external, parallel and serial flash. We have driver sources for all interfaces we have on our device. Everything is combined into an IAR embedded development environment, and we have also debugger support for various types of debuggers. On the last foil I show you the roadmap of our CC-Link IE devices. So for RIN32M3 we have a successor which is called RIN32M4-CL2. So this is a device which has a basic structure of the old device, but with a much higher CPU performance due to the Cortex-M4 CPU. This also includes the 2 gigabit PHYs, which enables you on the one hand side for further cost reduction, and on the other side this enables you to develop a much smaller board for a CC-Link IE application. So this was my presentation. Thank you very much for listening, and goodbye.